Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll explore parallel computing on CPU cores using OpenMP, Open Multiprocessing, on the Betzy Linux cluster. Our previous experiment on the Fram Linux cluster involved testing with up to 32 threads. Now, on Betzy, we'll extend our investigation to explore the effects of utilizing up to 128 threads. We'll use the Betzy Linux cluster for parallel computing with OpenMP, so let's log in. Upon logging in, we'll encounter a welcome message containing useful documentation and support details. Additionally, we'll receive updates from the ops log, along with any important notes and warnings. The Betzy Linux cluster, named after the first Norwegian woman awarded a doctorate degree, stands as the most powerful supercomputer in the Norwegian e-infrastructure. Located at NTNU in Trondheim, it serves as a vital computing resource. Betzy consists of 1,338 compute nodes, each equipped with 128 CPU cores and 256 gigabytes of memory. Additionally, it includes 4 compute nodes featuring the NVIDIA A100 GPUs and 6 nodes with 1 terabyte of memory. Before we begin, we need to transfer our Fortran programs and Python scripts from Fram to Betzy, following the same process we used to transfer files from Saga to Fram. We'll use the same matrix dimension as in our last test on Fram, as discussed in our previous video. It's essential to set the value of n to 16384 in our Python testing script for accurate performance calculations. For more accurate results, we'll execute the Fortran program 3 times and then calculate the mean wall time. We'll use the thread numbers specified in the threading array. Starting with a single core test, represented by threads equal to 1, we establish our baseline. For each thread number, we'll execute the test 3 times to calculate the mean wall time. It's worth noting that we can now utilize up to 128 threads. We'll stick with the same compilation options as used on the Fram Linux cluster, but this time we'll utilize the X host option. This decision is due to the absence of any march option in the Intel compiler for the AMD architecture type on the Betzy Linux cluster. We're double-checking the matrix dimension in our Fortran program to ensure its accuracy. We'll utilize the version of the Fortran program where both the initial loop and the matrix multiplication loop utilize OpenMP. This version enables all parts of the program to be executed in parallel. On Betzy, we have access to a range of job types, and for our current task, we'll specifically choose development jobs. These jobs are well suited for our needs and offer the ideal environment for conducting testing and development activities. We'll move to the standard compute nodes using our setup Python script. Here, we'll request one node equipped with 128 cores to conduct our OpenMP tests. Additionally, we'll indicate that our interactive job should wait in the development queue. To streamline our workflow, we'll utilize the Intel alias to access the latest Intel Fortran compiler and the matplot alias to access the newest versions of the matplotlib and NumPy modules. I've added these aliases to my bash.rc file on the Betzy Linux cluster, just as I did on the Fram Linux cluster. The Intel alias is configured to load the latest Intel 2023B module and other relevant modules. Similarly, the matplot alias provides access to the latest matplotlib and NumPy modules for the Python testing script. We employ our setup Python script to transition from the login node to a compute node. It's crucial to conduct both the compilation and execution of the Fortran program for matrix multiplication on the compute node, utilizing our CPU quota. After a brief waiting, we are directed to the B3248 node, where we'll continue with our multi-threading tests using OpenMP. We'll begin testing by using our Python testing script. At first, the Python script shows the compilation command, then proceeds to execute it. We'll analyze the executable program using different thread counts for testing. We observe an unexpected issue. The most powerful supercomputer in Norway appears to be slower than Fram. This result prompts us to investigate further into the performance gap between the two systems. There is also a significant slowdown on Betzy compared to Fram when using higher thread numbers. This discrepancy raises concerns as it contradicts our expectations. It's evident that something is not functioning as expected. Let's consider adding another option to the compilation command. We'll attempt to include the interprocedural optimization, IPO, and assess whether it can enhance performance. We execute our setup Python script. Shortly after, we'll be redirected back to the B3248 node, where we'll continue with our multi-threading tests using OpenMP. We'll start the testing phase by applying our Python testing script. At first, the Python script shows the compilation command before executing it. This is enabling us to view the compilation instructions, and we have now included the IPO option. It's crucial to compile and execute on the same compute nodes to avoid any discrepancies caused by potential differences in architecture between login and compute nodes. We'll analyze the executable program with varying thread counts. Now, we observe an improvement in performance, with Betzy completing the matrix multiplication faster than Fram. Therefore, the inclusion of the IPO compilation option resolved our performance issue. In this test, we witness a notable acceleration when shifting from 1 to 2 threads, with a performance increase of approximately 1.94 times. Moving from 2 to 4 threads, we notice a speed-up of about 1.91. The results for the other thread numbers are not shown here, but they will be included in the figure created with matplotlib. We use matplotlib in our testing Python script to create a plot illustrating the connection between wall time, CPU time, and the number of threads used by our program for matrix multiplication. First, we'll display the wall time values in the figure. Next, we'll display the CPU time values. We'll complete the figure by adding the speed-up values alongside the wall time and CPU time data. It's evident that multi-threading shows good performance up to 16 threads, but there's a slowdown when transitioning to more than 32 threads. This highlights the importance of optimizing thread count for efficient parallel execution, as excessive threading can reduce overall performance. Additionally, the figure illustrates a significant increase in CPU time when moving from 64 and to 128 threads, indicating a wastage of CPU hours from my CPU quota. We observed a notable performance enhancement when utilizing the IPO option during compilation on the Betzy Linux cluster. Now, let's assess whether this option can similarly improve performance on the Fram Linux cluster by incorporating it into the compilation command. As with previous tests, the Python testing script will execute the program with varying numbers of threads and calculate the mean wall time based on 3 tests. We notice some minor performance improvements compared to the test without using the IPO option. Improvements are also noticeable for higher thread counts, except for the highest thread count of 32. This highlights the dependency of the optimal compilation options on the Linux cluster architecture. While including the IPO option was crucial on Betzy, it didn't yield significant benefits on Fram for our matrix multiplication task. In our next video, we'll explore how to enhance OpenMP performance by utilizing thread affinity. This technique involves controlling the assignment of threads to specific CPU cores, optimizing program execution by leveraging hardware characteristics. By strategically placing threads, we can improve cache utilization and memory access patterns, ultimately boosting parallel computing efficiency. We will begin our OpenMP affinity testing on the Fram Linux cluster. I am looking forward to the next video, wishing you all happy computing in the meantime.